So, at least where I go to school, it is that time of year where everybody in chemistry is doing something difficult. My organic students are doing spectroscopy, which is a whole handful, but I made videos on that, so time to turn to the difficult things that my Gen Chem students are doing. I'm going to make a sequel to my long ago pH video and talk about pH in the general chemistry / mathematical sense. So I guess this is pH part 2. So, we talked in the last video about how there's this equilibrium between water, 2 of them actually, and a couple of ions, hydronium and hydroxide. And we can make an equilibrium constant equation out of this. And because water's a liquid, we ignore it. So we say that Kw, as we're going to call it because it's water, equals just concentration of hydronium times concentration of hydroxide. So we just omit water. And this is going to be equal to 10 to the negative 14. Now, something that's important is that this is only the case at 25 degrees Celsius. Equilibrium constants change by temperature. They don't change by if you change H3O plus or H minus or whatever, but they're going to change if I go to like 30 degrees Celsius or 100 degrees Celsius. It's going to change, and if they give you a problem where the equilibrium constant is not 10 to the negative 14 because you have a different temperature, then what you do is you're either going to get this or that, and then they'll give you what the new one of this is, and then you solve for whatever you don't have. Or maybe they won't give you this, but if they say, oh, pH is neutral at like 7.5, then what you do is, because P is negative log, pH equals negative log of H3O plus, then to undo the negative log, you say 10 to the negative 7.5, and that you plug in here, and you plug in here, and then you can get Kw, whatever it may be. So that's just really quick how to do problems where Kw is different at a different temperature. But those are actually pretty rare. The common problems come with either strong acids and bases or weak acids and bases, and molarity of what the concentration of H3O plus or OH minus is going to be in the end. So for strong acids and bases, strong bases, I'm going to start with bases because they're easier to remember, are any metal, so this M plus is a metal with an OH minus. So this may be NaOH or KOH or whatever else. It can be like calcium hydroxide. Although I don't know if that's soluble. No, it is soluble in water. Okay, anyways, so strong acids are kind of more complicated because you have to memorize them. So there's the whole bunch of halogen acids, so HF, HCl, HBr, HI, and you just name these hydro whatever acid, hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And then you have some with polyatomic ions, so there's like sulfuric acid, nitric acid, and chloric acid. And those are all strong acids. And the reason why I say this is because in our generic equilibrium where we have an acid, and this goes for bases too, their equilibrium is different, though. In our generic equilibrium where we have an acid and it goes to H3O plus in the conjugate base, sometimes this equilibrium doesn't go to completion because it's an equilibrium. With strong acids, they're going to so much favor this direction that it's basically not an equilibrium. We can cross out this arrow and pretend it's just, it goes. That means that if I have, let's say I have nitric acid, right, which is this guy here. If I have 1 molar nitric acid, so now the A is NO3, right? Then I know that I'm just going to like react this whole thing. And I'm going to get 1 molar of H3O plus and 1 molar of nitrate, which is the conjugate base. So molar works like moles in stoichiometry, where you can just like use the coefficients as a ratio. So if somebody asks me what is the pH of a 1 molar solution of nitric acid, I just do this, and then I take the negative log, and the negative log of 1 is 0 because 10 to the 0th power equals 1. Anything to the 0th power equals 1. With weak acids, it's different. So with weak acids, the equilibrium doesn't go to completion. Some of your acid reacts and some of it doesn't. And then we have to do this weird thing. So let's do a practice problem. I've looked up some pKa's, and I'm going to explain what I mean by pKa in a minute. And there's one acid, it's a weak acid, and it's called thiophenol. And this is the proton that goes. So this is C6H5SH. And the pKa for this is going to be 6.6. So I want to know if I start with 3 molar of thiophenol, what's my pH going to be at the end when I've reached equilibrium? So in these acid and base problems, you're going to have an equilibrium constant, and that equilibrium constant is either going to be called Ka or Kb, and the A and the B just mean acid and base, and it depends on if you have an acid or a base. In this case, thiophenol is an acid, and I'm telling you that in the problem, and they would tell you that in the problem. So the Ka is the equilibrium constant. Now, when we said pH, the P meant negative log of H. Here, the pKa equals the negative log of the Ka. And how do we undo negative log? We do 10 to the negative whatever it is. So we're going to do 10 to the negative 6.6. And what we're going to get out of that is 2.51 times 10 to the negative 7th. And I know my times symbol looks like a decimal point, but I like to do that to avoid doing an x, because then you get it confused with the variable x, which we will use in this video. So now that we have our Ka, what can we do? Well, we're going to use a tool that is known as an ICE table, and ICE stands not for the Immigration and Customs Enforcement, thank goodness, but for initial change in equilibrium. So what we're going to do is, I forgot to put water into this equation, but the thing is that we don't care because it's a liquid and it's not going to be included into the equilibrium constant. So when we make our table, we're going to have HA, which in this case, I'm actually going to write out the formula for thiophenol is C6H5SH. And then we're going to have our H3O plus and our conjugate base C6H5S minus. So this H went away and joined the water to make hydronium. And whenever you do these equilibria, you need a plus and a minus in the end, because according to conservation of charge, which says we need the same charges to add up on either side of our equation, we have a 0 and we have H3O plus that we make, so we need a minus. Anyways, so then we have I, which is initial, change, and equilibrium. So I, C, and E. Okay. And then we're going to make our little table. And we know that initially we have 3 molar of thiophenol. We also know that, like, the minute that we put thiophenol into our solution, we're going to assume that we don't have any H3O plus. And I know that the equilibrium for water says that we always do have H3O plus, and that, like, we have 10 to the negative 7th power of it in a neutral solution. But the assumption that we make in these problems is just that we start with 0. And then we also start with 0 of thiophenide, or whatever the conjugate base might be called. So now we have to look at the change. We don't know the change. That's why we're doing this table. So we're going to say that we use up X amount of our thiophenol. So I'm going to say minus X, because we're going to end up with less of it because some of it reacted. Likewise, we're going to end up with positive x more of each of our products because we are making some of them. And the sum of them has to be stoichiometrically equal to how much thiophenol we lost because they all have one coefficient. And then in equilibrium, all we have to do is add up our initial and change. So 3 minus x, and I'm going to stop using the molar unit because it's just going to make things complicated to have an extra letter in there. And then we have x here and x here. So now we need to do our equilibrium constant. So equilibrium constant is products to the powers of their coefficients over reactants to the powers of their coefficients. But excluding or omitting the solids or liquids, since water is a liquid, we omit it. All the others are aqueous, so aqueous and gaseous things we include. So our products are H3O plus and not OH minus, come on. It's going to be C6H5S minus. That's what we're making. I'm too stuck on KW. And then we have thiophenol in the bottom. So we can put numbers into this now. And these numbers are going to be that our Ka was 2.51 times 10 to the negative 7th power. And then we have X as our hydronium, X as our conjugate base, and 3 minus X as our concentration of thiophenol. Now X times X is X squared, so we can fix up this top and simplify it. Now, how do we get X by itself? This is a quadratic equation. So if you don't know quadratic equations, go learn about quadratic equations because as much as I know about math, I'm bad at teaching math. So I'm not going to teach you math. But anyways, what you do to get X organized here is you're going to multiply by this. And so if we multiply by that, we're going to get this. Okay, so now we distribute. And then we have to do some math. I'm going to multiply this out. So then we get this, and then we can, I'm going to just subtract everything on this side to the right. So then it's going to be 0 equals X squared plus this minus this. Okay, so now we have a quadratic equation. Now, we can't factor this. We're not going to factor scientific notation, but lucky for us, we know the quadratic formula. Quadratic formula, as a reminder, is x equals negative b plus or minus the square root of b squared minus 4ac, and these a's and b's and c's are just our coefficients, over 2a. And so there are quadratic formula calculators online. When I do ice table problems for my students, when I've done like tutoring, assessment exams and stuff, what I do is I just use a quadratic formula online. If you are taking a test for a class, I would suggest that you program this somehow into your calculator. Like in my calculator back in the day when I took tests on this stuff, I would have a way to put in A and B and C, and it would spit out my 2 possible answers. And there are going to be 2 possible answers, but if you do this right, one of them is going to be negative. And can molarity be negative? No, it cannot. So in this case, A is 1. A is pretty much always going to be 1 in these problems. B is this, and then C is that. So pop these into a quadratic formula calculator, and what you get is one of your answers is 0.000868. And remember, this is molar because we're solving for concentration. The other answer is negative, and that's not going to be the answer because you can't have negative molar. So I want pH, right? This is the concentration of H3O plus. And it's the concentration of the conjugate base, but we don't care. But It's the concentration of H3O plus. How do you get pH from that? Well, H plus and H3O plus are pretty much synonymous, and pH is log of H plus, or negative log of H plus, because P is negative log. So we're going to take the negative log of this number, and that will get us the pH of this solution at equilibrium. And that number is going to be about 3.06. And that makes sense because it is acidic, which means it's below 7. So now we're going to do an example with a weak base. And I'm going to stick with my theme of benzenes because we had thiophenol last time. And we're going to talk about aniline, which looks like this. So whenever you see a nitrogen in chemistry, it's going to be basic, especially in like this acid-base chemistry. You hear nitrogen or you hear amine, you think basic. So this is called aniline. And the formula for it is C6H5NH2. And so it's going to gain a proton and become C6H5NH3 plus, because protons are plus. And I went and I found it's Kb, so we don't have to calculate from pKb this time, just a Kb. And it's going to be 7.4 times 10 to the negative 10. Now this looks like a very small Kb, and we might think, oh, that means it must be acidic and not basic. Not true. So you can have a Kb be like smaller than it's supposed to be, or smaller than 10 to the negative 7, and it could still be basic. So let's look at our equation. It's going to be C6H5NH2 plus water, which we don't care too much about, is in equilibrium with our conjugate acid and hydroxide, which is what we get when we do a base. So we're going to construct an ice table. I forgot to assign us a problem. We're going to look for the pH of a 0.2 molar solution of aniline at equilibrium. So let's do that. So we know that the initial concentration of aniline is 0.2 molar because I just told you that. And we know that we start with 0 of this and 0 of this, and that we don't want to include that. Okay, so our change, we don't know, so it's going to be minus x from the thing we're using up and plus x for the things that we are making. Equilibrium, 0.2 minus x, x, x. So you see we start to get into a routine. So the Kb is going to be equal to our conjugate acid times hydroxide divided by concentration of aniline. Oh, not H3, NH2. Okay, so now we can replace these with numbers. So we know our Kb was 7.4 times 10 to the negative 10. And that's going to be equal to x squared, because we have x times x, over 0.2 minus x. Okay, so we can do this out, and what I'm going to do is pause the video and then write out a bunch of it. It's the same algebra as we did before. So here's what I got for the answer. I solved the equation, I put it into a quadratic formula, and now I have this value for concentration of OH minus. So from here, what we can do is get the POH by taking the negative log. So if I do negative log of OH minus, which is negative log of the thing we just got, what it gets us is 4.91. So a lower P whatever means you have more whatever. So a lower pOH means we have more OH, which makes sense because we put in a base. But the question asked for pH. So how do we get pH from pOH? Well, you know how H3O plus and OH minus concentrations have to multiply to 10 to the negative 14th? Well, it turns out if we do some logarithm math there, the pH and the pOH have to add up to 14. So pH plus pOH equals 14. So pH plus 4.91 is equal to 14. And if we subtract 4.91 from both sides, then what we're going to get is 9.09, which is greater than 7. pH greater than 7 is basic. So that makes sense. So now you know how to find the pH of a solution with a weak acid, or a weak base, or a strong acid, or a strong base. I think we went through all cases except for the strong base, but that works the same as the strong acid. So have fun doing these problems on your own.